we arrived at a point where we had multi-particle superfields of the same type as of the single particle fields of super-individuals, and where this P is a multi-particle label. And the whole set of superfields, they satisfy generalized Jacobi identities. Generalized Jacobi identities. And well, it was quite a battle to arrive at this structure. It required doing some calculations at lower points and trying to simplify the answer and look at the structure. So today we are going to make use of these multi-particle superfields, and we hope. And today I think all the n-point amplitudes in super-n views and the string tree-level amplitude will be written down. And just to remind, let's just take one example of this structure here. Oh, and okay. For example, we had these multi-particle with labels 1 and 2, and then the Jacobi identities allows us to simply get rid of the brackets, because we know that this guy is antisymmetric. And well, that's more or less of a convention to get rid of the brackets once we already redefined the superfields to be in the BCJ gauge. And a surprising feature of these multi-particle superfields is the kind of equations of motion that they satisfy. Say, for example, this one is something like, so they are all intertwined by the equation of motion. So, and then plus a contact term. Right, so we have a nice set of superfields, and in okay, so yeah, I think but this structure was found when doing the computation of the string correlator. So the string correlator and the claim that I'm going to make here is that the string correlator assumes a very nice form when you write the result in terms of these multi-particle superfields. And then this is the only guy where I'm going to fix and C1 and Cn minus 1 in principle are fixed at 0 and 1, but I keep their labels there just to make the formula simpler. And the claim is that this correlator is equal to a sum over v from 1 to j from 1 to p. Okay, I'm sorry. It's p from 1 to n minus 1, n minus 2, and v1 to p over z1 to z2 3 z p minus 1 p. So notice that I don't close the cycle if there was a p1 here, it will close the cycle, but there is no such factor here, and that's very important. So I have this guy, and then the other factor is n minus 1, n minus 2, up to p plus 1. And then the same structure here, but now with these labels.
Carlos, can you write a bit bigger? This.
Oh, yes.
This downstairs.
Yeah.
So we can just multiply. But that's kind of.
Well, okay. It's too late. So I was noticing that I was going down the slope, so 1, 2, p, c, 1, 2, c, 3, p minus 1, and then p. And okay, so there is the spinor bracket there.
Z1 to Z3 4, right?
Z
3 4, right?
Yeah, there is a 3, 4, and all the way to p minus 1p.
Yeah, but there is no 2 3. Right?
Yeah, it's 2, 3. And then the next one is 3, 4.
The first
What?
one will make it Z2. The first one will make it Z2 and then Z2 6.
Okay. And then b n minus 1, n minus 2. I'm writing the comma just to separate the labels, but and then up to p plus 1. It's I hope the notation is clear. This is a single particle label, and then the same structure of z's in the denominator. Z n minus 1, n minus 2, and then z n minus 2, n minus 3, up to z p p plus 1. And then everything multiplying the v and standalone, and plus permutations of the labels 2 to n minus 2. The labels associated with the integrated vertices. Okay, so I close this guy here. Yeah, okay, so something like that, and then multiplied by the Copernican factor. So that's the correlator. And yeah, so everything you need to know about the string 3-level amplitude is here, but I'm still going to show that there is a very nice simplification that you can still do here, and rewrite the whole thing in terms of super and mu's 3 amplitudes.
So what is the last one? P.
The permutations.
Permutation of
Yeah,
mu 2 and minus 2. Or mu.
Starting with 2. Permutations we should write like that. 2 and minus 2 and then.
Here, color factors are already included somewhere.
Yeah, okay. The color factors, they are included. Well, they are not here. They don't appear here. They are outside. The whole thing outside.
I'm just wondering that why we have full permutation symmetry under 2, 3, 2, and minus 2, because normally it's cyclic permutation, right?
Yeah, but it's these guys are bosonic, right? So it's symmetric in 2 and 3 over there.
But that's only after you also extend the color factors.
Yeah. So these guys do not contain color factors. The color factors are sitting outside. There is a trace over T1 to Tn outside.
So when you sum over permutations, you also permute the color factors?
Let me see.
There should be no problem.
No.
I see. But then isn't it surprising that there will be a permutation symmetry in 2, 3 to 4? Because normally it's cyclically permuted.
No, yeah, so the whole thing has all the symmetries that you would expect, but it's just these symmetries here that are manifest. The other symmetries, say for example, when you change, if you want to check cyclic symmetry, for example, then it's a bit more complicated to show because you need to do integration by parts in the BRST charge.
But see, if you have this, right?
Yes.
And the whole thing is multiplied by that trace, then it's not symmetric under 2, 3 permutation, right? Because the thing inside the square bracket is invariant under 2, 3 permutation, exchange, but that one is not.
Okay, let me try to make it more precise and see. Then we are completing the string amplitude with say a color ordering in the canonical ordering like that, and that is this ordering here will be associated to the integration region of the integrals, right? So and of this correlator there, and the full amplitude is that so, and the full amplitude is a sum over the cyclic the n-1 factorial permutations of trace T1 up to Tn of that guy.
And what you have written here is just A, this factor is...
Yes, yes.
Is
So this is the integrand.
because then it looks a little surprising that we have commutation under 2, 3. Because if this is not symmetric, that should be there, right? The exchange of 2 and 3.
Yes.
From the point of view of the open string diagram, they are cyclically inserted on the disk.
Yes.
Right? Like 1, 2, 3, 4, 5. So why are you getting this 2, 3 permutation symmetry?
Well, let's try to.
In your A string, there is a ordering, na? Z1 less than Z2 less than Z2.
Let me just write down the.
Which is not permutation symmetric. A string has these ordering on Z.
Okay.
That is not permutation symmetric.
So that's some of this one.
Yes, right.
So it's an accident.
A trace will be multiplied to this one.
Like this. And then
Where that is
And then the only integral that I need to do here is really z2. And z2 I can put between 1, z2, 3, and 4. And I integrate here. And so that's the string in the ordering 1, 2, 3, 4.
Yeah. See, for 4, I think there is a confusion because there is only one unintegrated part, one integrated vertex operator. Right? For in this case, there is only one integrated vertex operator.
Yes, yes.
Yeah. But I'm just confused about here that you have say n minus 3 integrated vertex operator. Right?
Yes. N minus. Yeah, n minus 3.
Yeah, 2 to n minus 2, right? Those are integrated vertex operators.
Yes.
And you have added permutations under 2, 3 to n minus 2.
Yes.
Right? So this is what is confusing me. In general, there is no reason why that symmetry should be there. Why there should be symmetry under 2 exchange of 2 and 3. Because this particular amplitude is, if you look at it on the disk, there is no such symmetry, right?
But
it has a cyclic symmetry with all n.
Yeah.
Not otherwise, right?
Yeah. I mean, it could be it's just there accidentally, that it's not inherited from any symmetry of the original.
I mean, it's a correlator, and then, for example, what would be the difference if instead of writing these, you would write U3 and then U2, Z2, and then do the computation? No, it should be the same correlator. The color ordering is outside.
So if I just CFP correlator, it will be the same.
Yeah,
The CFP correlator.
the CFP correlator is the same. And so that's what it's.
There is no sign or phase or anything. Typically, there could be additional phases.
Oh, the co-cycle factors,
Yeah.
I guess. But
Yeah, okay. Maybe in this case, you are saying there is nothing that we just add everything to computation.
I mean, I don't see why these two CFP correlators would be different. Just computing with U2, U3, and then U3, U2. And it is, yeah, so the symmetry is there. It's, so let me just write down another example. So this is how the 4-point.
Sorry, there's no permutation for the 2-point, for the 4-point, right?
Yeah, but then there is this sum still.
Oh, okay.
So p from 1 to n minus 2.
Okay.
Yeah, so there are two terms. So in general, there are n minus 2 factorial terms. In this, there is a sum and there is this permutation.
But will the final answer have symmetry?
What?
If I plug this answer into there, will I get symmetric answer? Like the full answer?
Oh, okay. Yes, the answer is yes. for example, this guy here, well, but okay, I can rewrite this as, I'm going to rewrite this as S12 over Z12, then the young is M2, 1, 2, 3, 4. And then this starts as the young views amplitude, and then alpha prime squared as zeta 2, S1 2. So it's
that will be saying that you Z3 U2 if I change the order of that format, if I exchange Z2 and Z3, which is the argument of U2 and U3, then also it will be same.
okay, no, but then you can do crazy stuff like I'm computing U2 and then put that position n minus 2 and then, but you can do complicated stuff like that, but in the end it's just a renaming of labels. But okay, I thought that was supposed to be here, but okay, so this formula for 4 points generates this expression, and I'm just going to write down the 5 point. Just to get a feeling of the patterns. Then plus 2 and 3 and covariant factor.
So if you have this many symmetries, in each color ordered amplitude, how many independent factors are there? What are the?
What?
So if you have permuted symmetry and plus like all this symmetries, in each color ordered amplitude, how many independent factors are there?
N minus 1 factorial. It's the cyclic.
Yeah.
It's the cyclic orbit. But okay. Okay. So this symmetry n minus 1 factorial is in some sense. Because of the property of the trace. But then you can still use these formulas, but I don't think I will have the time to show that. To show that, well, in the field theory limit, only n minus 3 factorial color ordering survive. But that's it will go too deep into technical details. I was thinking of motivating just as a mnemonic way to compute this correlator using the superfields in the BCJ gauge, and the way to do this is you define the OPE for arbitrary multiparticle A and B, so that this is the OPE of V A B over C A B, and similarly like that. So yesterday we the last time we did a computation when A and B are single particle labels, say 1 and 2. Then we got that, but let's generalize for multiparticle labels. And so now A and B can be bracketed themselves. And so and there would be a double pole here, but let's kill it, and killing it means we're going to use BCJ gauge for the brackets. So let's just see how this works in practice to derive that. Say, for example, we want to compute the 5-point.
Sorry, what did you write that you crossed out this last?
Oh, it's the double pole.
Double.
And then we eliminate Z2. Let's start with Z2 and use those guys. We get 1, 2 over Z1, 2, and then U3, V4, V5 plus V1, and then U, now it's 3, 2, V4. I'm not going to write V5 to save space because it's V5 is at infinity and doesn't take any OPs. And then plus, so okay, over Z 3, 2 plus V1 U3 V 4, 2 over Z 4, 2. That's the first step where we eliminated Z2. And now, for example, this guy is still at Z1 and this is at Z3, so that there is no Z2 anymore here in the numerator. So now we eliminate Z3 using those rules. And we get V 1, 2, 3, V4, Z1, 2, Z1, 3. So you see it's 1, 2, 1, 3 because we are eliminating Z3 and this guy is at Z1. So you get 3, 1, 1, 3 here. Right, so but you see that in the answer we have 1, 2, 2, 3. So and there is something that will happen later. And then similarly we get this guy from there. See 1, 2. 4, 3, and plus C 3, 2, 0, 1, 3, and yeah, Okay, so now there are other three terms, but they are not going to matter for the discussion that I'm going to do in the sequence to get these terms, because they the terms that I'm omitting here, they can be derived using these formulas, but they will give rise to that term, but I will zoom in into that term. Okay, so we see that the bracket structure is 1, 2, 3, and then 1, comma, 3, 2. And then we have these see 1, 2, 1, 3, and so forth. But now we use the fact that the string correlator, because of the double pole and all that, wants you to be in the BCJ gauge, where you can use the Jacobi identities for the brackets there. So V 1, 2, 3 becomes this is the trivial one, but V1, 3, 2, that's there are several ways to do this, but this one becomes 1, 3, 2 minus 1, 2, 3. And so now we collect, say for example, V1, 2, 3 in the correlator there. So we have this term from the first one minus, because of that minus, this guy. And now you see what happens, because you use partial fractions. The partial fraction identity is obeyed by these guys, and this becomes which is the first term there. And similarly, you do that, and you see that there will also be a 3 and 2 permutation, and the 3 and 2 appears only once, but it's already with the correct pole, the function there. It appears with the permutation. Okay, so we I hope to have motivated you that this is the CFT correlator, and well, it's the general result, and but now I need to tell you about super and Mills amplitudes, because we are still going to rewrite that correlator in a more convenient way. So any questions? Not about symmetries? So we have the full set of multiparticle superfields, but now I'm going to focus on only one of them, A alpha P. And this guy here, multiplied by the P spinor, is defined as the VP. And the BRST variations of these guys, well, the single part one is closed. The V12 is S12, V1, V2. then this one is A1, A2, V1, V2, 3 plus V1, 3, V2 plus and so forth. I wrote the general formula last time. There was the power set convention for dealing with these permutations here. And okay, so what we want to do is we want to find an expression for the super-ambiguous amplitude at tree level. And it's convenient to use a representation for these amplitudes that was proposed by Bernd, Carrasco, and Johansson in 2008, where they simply proposed a cubic graph expansion of the amplitudes that emphasize the pole structure of the amplitude. So, for example, the 4-point amplitude with this color ordering, you write it as something like this: 1, 2, 3, 4 plus 2, 3, 4, 1, and these are not Feynman diagrams because in principle you would have the quartic interaction, but the trick that they use it is that they absorb these guys into these. For example, they multiply. You can do these, and then absorb this term into here or there by multiplying by 2 and 3. So that's a way to organize the amplitudes, and we see that well the amplitude will be something that contains these two poles, and we know from the string theory computation that whatever will happen with the integrals in the field theory limits, the result will still be written in terms of 3 V's, right? So and the string amplitude is BRST invariant. So let's try to use these two facts to write down something that is BRST invariant there.
The 4-point diagram you said what will be like? Not something that the 4-point gap something. You said there will be a 4-point diagram.
Oh yes. If you, I just said that because that will be the quartic interaction from Feynman diagrams. But these are not meant to be Feynman diagrams. They are just a way to organize the computation in the sense that you make manifest the poles of the amplitude. And
so there will be a 2-4 type of diagram where 2 and 4 come together and 1 and 3 are that part.
yes, so you write down everything that's compatible with the color ordering. Yeah.
So what you are doing is giving an alternative way of deriving this result from consistency, is it?
What?
Because earlier you gave a derivation, right, for the endpoint function.
Yes, yes.
Now you want to re-derive it by using consistency.
Yes. So and because that's historically how it happened. We first guessed the endpoint super-ambiguous amplitudes by consistency, and then when we arrived at this computation, At a later stage, we identified that we could rewrite these guys in terms of those amplitudes. But so there was a decision that I had to make in trying to explain this. I could have started with the Young-Mills amplitude and then write down the correlator and then already do the identification, but I chose that order. But it's a bit non-linear because everything was happening almost at the same time. So the 4-point amplitude here is simple to guess what's the result. It's that one. Why? Because it's BRST closed. Say this first guy here, Q V1, 2, V3, V4 is over S1, 2. You use that, it's V1, V2, V3, V4. And then this guy here picks a minus sign because Q1 commutes with V1. So the BRST variation of this guy, Q is minus V1, V2, V3, V4. So it's BRST closed, and we are going to see later that it's not BRST exact. So it's in the homology, and since it's in the homology, it's gauge invariant and supersymmetric. What?
Those are cancelled. S1, 2 are cancelled. Q1, 2 and S1. And the minus sign we got by commuting to Q1?
Yes, because when I hit it's Q here, so actually it's it's the whole integrand that should be closed. Right, so this one, it's simply cancels that pole and gives you V1, V2, V3, V4. But then when Q acts on this guy, the first one is 0 because Q of V1 is 0, V1 is BRST closed. And then it anti-commutes with V1 to hit V2, 3. And then it cancels the pole, but you get the minus sign. So the idea is really to see that the amplitude has the correct pole structure and it's supersymmetric and gauge invariant. So it should be the correct amplitude. That's kind of a conjecture at the time it was proposed, and it turns out that, well, at this point you can use the component expansion to check that it works, and it works. So so the answer is very simple. And now, for example, you try the 5-point amplitude, and you see that there are 5 terms, and they have this structure: 1, 2, 4, 5, and then plus cycling. This is also BRST closed and has the correct pole structure. So the idea was to say that this is the correct Young-Mills amplitude. Turned out it is. But you could, okay, so this one, for example, comes from this cubic graph. So, and just to, as a brief side comment, there are 2 kinematic poles in the 4-point amplitude and 5 kinematic poles in the 5-point amplitude. And in general, these numbers are given by the Catalan numbers. So, Catalan numbers. They start with 2, 5, 14, 42, and then I forgot, it's 128 or something, but
So this is number for what? Sorry,
so these numbers give you the number of different kinematic poles in the amplitude, in a polar order in the amplitude. So there are 2 poles for the 4-point and 5 different poles for the 5-point. But now,
So these kinematic poles are obtained by drawing all possible diagrams and then seeing how many denominators you have
yes,
for a given cyclic symmetry.
yeah. Say for example for 6 points, one possible guy is this one, but then there is also a snowflake. And these are the only topologies of diagrams. But then the permutations here will give you 14 different poles.
Why is it called Catalan number?
Because it was Catalan who discovered. Well, it's, I don't know.
I'm asking whether there is any different mathematical background or not to these numbers.
Well, if you look at the book by Stanley, I guess, in numeric combinatorics, he has like 120 something interpretations for the Catalan numbers. There are all kinds of combinatoric identities associated to these numbers, and this is one of them. So there are a lot of things there, but there's not enough time to discuss them.
If somebody tells you instead of 14 it was 13, how do you know? Just tell me what formula to get this.
Oh, okay, yeah. So yeah, that's what I am trying to do now. Well, in a few moments. Okay, so one thing that you can start to play with is you start to divide by Mendelssohn invariants, these guys, and then you define new objects like these. Why you do that? Because then Q M1 2, and then okay, you define M1 to be V1. And I'm using 1, but it's really a single particle label, so Mi is Vi. So, and then you get this structure here. And similarly, well, I do this because that's a type of pole structure that, well, it's suggested by the amplitude. So the next one, you do this. Why? Because then Q of M1 to 3, I'm not going to do the computation, but the answer is very nice. You get this deconcatenation pattern. And so the next one is a bit more complicated, but now I'm going to tell you what's the general pattern here to construct these guys. And yes, but the
What was the definition of S1, 2, 3?
oh, the S1, 2, 3 is it's 1/2. So it's my conventions is S1, 2, S1, 3, S2, 3. So how can you construct, how can you know the expressions here? One way to do this is by using a technique with planar binary trees. Which say, for example, the first case there, a planar binary tree is a tree with cubic vertices only and one leg which is special and it's called the root. But then there is no label associated to the root. And this guy you map to V12 over S12. So S12 you see is the momentum flowing in the root. And then you simply associate the bracket structure to the branching of the trees. So and by the way, there are the Catalan number of planar binary trees as well. So the next one is there are 2 binary trees, and then you sum them. 1, 2, 3, and then you say that this guy is V 1, 2, 3 over S1, 2, S1, 2, 3. So the momentum from here and the momentum from there, and then plus V with 1 and then bracket 2, 3. So you see that I simply write down all trees and map to the vertex with the same bracket structure. So M4. So and then these define M12, and then this defines M1, 2, 3, and then M4 will be given by a sum of 5.
Roots are the ones which form the internal lines. Then what is the distinction between roots and?
The root is this guy here, and that
that vortex actually. Only one vortex is there.
Yes, only one, yes. And then so these five diagrams define M1, 2, 3, 4, which, for example, that one will be V1 1, 2, and then comma 3, comma 4 over S12, S1, 2, 3, S1, 2, 3, 4. and similarly for the other ones. And I think it's a very non-trivial statement that you now rewrite the brackets here using the BC the Jacobi relations, and then you compute Q of the whole thing, and then you see that Q of M1, 2, 3, 4 is M1, M2, 3, 4 plus M1, 2, M3, 4 plus M1, 2, 3, M4. So it's a nice pattern. And yes, so once you do this, you get the general structure is that Q of MP is equal to all the deconcatenations of the label P into 2 Mx and Y. So is this notation clear to everyone, that you deconcatenate the label P? Say for example, okay, I'm going to do when P 1, 2, 3, 4. So you get X can be 1, and then Y 2, 3, 4, X 1, 2, 1, 3, 4, X. So these are the three terms in the sum that correspond to that kind. And okay, so when after you do this and you play around with the poles and the RST invariant quantities, you arrive at the proposal that the ambiguous amplitude can be written as x, y, 1, 2 to n minus 1, mx and y multiplied by m is and it's convenient to define this combination here as E. You just say that this is E 1, 2, 3, and minus 1, and then, for example, you can check that Q of EP is 0, and yeah, okay, so that's or Vn is the same thing as Mn because it's a single particle label. So so what about the Catalan numbers? Let's just count the number of poles here in this definition. I will just do a few examples and then the general formula is will follow. But say E12 is M1, M2, so that there are no poles. E, and that corresponds to the 3 M1, 2, M3, and then you see that this is 1 plus 1. E1, 2, 3, 4 is M1, M2, M2, 3, 4 plus M1, 2, M3, 4 plus M1, 2, 3, M4, and then that's inside there are two poles, so it's 2, 1 because it's 1 and 1 there, 1 plus 2 because this is 1, 2, 3. There are two poles there, so it's 5. And then, well, you can see that, for example, the next one will be 5 plus 5 plus 2 plus 2, and then that's 14. And then if you just assign, if you just find a recursive formula for that, you arrive at the formula, at the recursive definition for the Catalan numbers. It's very interesting because there are many ways to write the Catalan numbers, but if you look at the original paper by Catalan, that's precisely how he obtained those numbers. Okay, so yeah, so for example, now you can simply say, well, the 5-point amplitude is this, and it makes sense. So it's you have all the nice properties that you expect. It's BRST invariant and has the correct number of poles. Then that's all the time. And okay, so now the superambiguous amplitude P level is known, and there is a very simple structure for it. And any questions? Oh, I forgot to mention something. You see that this is the same definition as E here. So why the whole thing is not BRST trivial? Because this guy is BRST closed and E is Q of something else. So for example, we all know that the 3-point amplitude is M1, M2, M3. But then you can say that, well, this is Q of M1, 2, M3. And all this time we are talking about the cohomology structure of the bracket, so this should be 0, right? But notice that M12 is defined as V12 over S12, and for 3-particle kinematics, S12 is 0. So kinematic phase space saves the amplitudes from being 0. So you are not allowed to use M1, M2 being Q of M12 for 3-particle kinematics. You are allowed to do that for 4 and beyond, but not for 3 particles. And the same thing, the same reasoning applies for the other ones. So M1 to 3 will contain this pole, S1 to 3. You can see there. And then for a 4-point amplitude, this guy is 0. So you cannot say that E1, 2, 3 is Q of M1, 2, 3 for 4 points. And so that's why this formula here is in the cohomology. The whole thing is not the BRST variation of something else. So so this guy is truly in the cohomology.
So this is like getting contribution from the boundary from this, right?
No.
This non-zero when S12 goes to 0, right?
What?
This, so you are saying that this is not BRST exact, it's not 0 because of this 1 by S12, right?
Yeah.
So that S12 goes to 0 is like going to the boundary to modulus, right?
No, it's just kinematics.
Which one?
Yeah.
Yeah, external momentum. This is
Yeah.
external momentum, right? So this is like factorization. I don't know, wait.
I think the part of it go slightly off shell and then you have to, he is saying maybe that if you go slightly off shell, could you have thought of this as a boundary contribution? Because slightly off shell, then this is not 0 anymore, right? S1 to 3 is 0 only when the external momentum are on shell.
Okay.
So if you go slightly off shell, could you have thought of this as a boundary contribution? Because it did look like that what you are picking up are boundary contributions. Because all the full answer was written in terms of the OP only, right?
Yes.
So could you have thought of that as some of boundary contributions?
I should say that I'm not being able to see what boundary you are talking about, but
Well, 2 points are coming close in a
Yes.
modularized space.
okay, so when vertices collide.
That's it, yeah. Because your final answer is expressed as the sum of terms like that, right?
Yes. But yeah, but I don't know really what to say. It's in the cohomology for the endpoint phase space, or and if you go off shell, then I really don't know what happens. Okay, so let me just come back to the string correlator and rewrite the whole thing in terms of Mu's amplitude. So it will be easier to do the first few examples explicitly, and then you will see the pattern of the manipulations, and then it's you understand the general form. So the 4-point integrand is this one. So now what we are going to do is we say V12 is S12 M12. It's just triviality at this point here. But then and similarly there. So the correlator becomes S12 over Z12, and then I'm going to write everything in terms of m's now. M3, M4 plus 3, 2, M1, M3, 2, M4. And I can using antisymmetry of M and Z to 3, I can write this as M to 3 and then Z to 3. And everything multiplying the Copernicus effect. So now I use that integration by parts that, this is the integrand, so that there is a total C2 integral to do. So I use this, which is S12 over Z12 plus S32 over Z32, and so inside the integral, I think we say that this is 0. So what this tells you is that say you see that it's S12 over Z12 is equal to S23 over Z23. And now you plug that back there, and you get the overall factor is this one, and then M1, 2, M3, M4 plus and then this is the Yang-Mills amplitude. So S12 over Z12, the Yang-Mills amplitude 1, 2, 3, 4. So that's the string correlator. And so just the immediate consistency check that the result is okay. You can verify that this integral of a Copernicus S12 over Z12 when the ordering is 1, 2, 3, 4, that's 1. You basically kill the pole by that one. So in the field theory limit, right? So let's see. So the correlator, the string amplitude, really goes to 1, 2, 3, 4 super-amplitude. But now something very, very nice happens at the next order, because here this rewriting was kind of trivial, right? So what should you use in the next step? And something very surprising happens. Plus 2 permuted with 3. That is S12 over Z12 S13 Z13 and 1, 2, 3 plus 2 permuted with 3. And so that's what we call the trading identity. Because we trade V's by M's. And it's quite a non-trivial identity if you think about it. Because just plug the expression for M1 to 3 there, and then you see there will be poles there, and like 1 over S1, 2, 3, and S2, 3. And then, for example, what will happen when you multiply by S1, 2, S1, 3, it doesn't cancel anything, but in the end, everything cancels and you recover that. It's quite remarkable. And okay. So the 5-point correlator had this structure. C1, 2. Oh, and by the way, it's very convenient to define, to say that this is x1, 2, and then this is x1, 3 plus x2. So x ij is Sij over Cij. And then, because you add this permutation of 2 and 3, you take this term and use that identity. So that becomes x1, 2, x1, 3, x2, 3, m1, 2, 3, then m4, m5. And then you get x1, 2. Now I think I might mess up some signs, but you get the idea. And yeah, and then these other terms there. But now I just want to focus on these two terms. The third term will perhaps I should do this. I'm waiting. So this one, you use an integration by parts with respect to position Z3, and then that becomes x3, 4. So it's the same guy over there. So the whole thing will be so this function here becomes the same function as that one, and it will become the same function that comes from the other term. So you get x, then m1, 2, 3, m4 plus m1, 2, and 3, 4 plus m1, and 2, 3, 4, and 5 plus 2, 3. And then this guy you identify as E1, 2, 3, 4. So what you show is that the correlator becomes x1, 2, x3, 4, 1, 2, 3, 4, 5 plus x1, 3, 2, 4, 1, 3, 2, 4, 5. Supreme is multiplied by Covariance factor. So without doing any other type of computations, you can immediately see that the basis of Yang-Mills amplitudes for 5 points is two-dimensional, which in this case it's n-3 factorial. Why? Because we are computing the string correlator with some ordering here. And this is fixed. And the ordering here will correspond to the ordering that you integrate over the positions, the insertions of the vertices. And we know that in the field theory limit, the string amplitude from on the left hand side must reduce to a Yang-Mills amplitude. And so that tells you that any ordering you choose to compute the string amplitude, you take the field theory limits, the result will be written as a linear combination of just two Yang-Mills amplitudes. So that's a derivation of the n-3 factorial basis of Yang-Mills amplitude. The BCJ relations. So you can, of course, you can study the integrals and actually get the relations among amplitudes like S12, S Yang-Mills 1, 2, 3, 5 plus some 0. You can get from there. Okay, so I'm just going to write down the general formula, and it will be starting point. So you can repeat this game for higher points, and then you realize that the pattern is this one. You get the integrals over the region, computations factor, multiplied by product of k from 2 to n minus 2 of a sum from n1 to k minus 1 s n k over c n k means everything. Yeah, that's the general endpoint and into that 3 level. The integrand, but nowadays people know everything that you can ask for about these type of integrals, the field theory limit, the alpha prime expansions, and there is a very, very nice structure that these particular combinations of integrals obey.
The last, that's what, n minus or 8 point.
Okay, you got that?
No, I was asking what you have written n point.
Oh, n points. The n point 3 level correlation. And yeah, okay, so that's that's an infinite set of amplitudes. And yeah, so in theory, you could have obtained this expression using the RNS, because the RNS formulation, well, in principle, in theory, everything is known, you know, the correlators and all that, but okay, so yeah, but in theory, theory and practice are okay, no, I forgot to, I had this because it's a famous, in theory there is no difference between theory and practice. In practice there is. That's a quote by Yogi Berra, which by the way was a famous New York Yankees player. So yeah, let's stop here.
Similar formula for closed strings?
KLT.
And the KLT gives you the closed string from here.
Yeah.
From RNS formulation, these are can one derive this from using this monodromy relation?
From
Using monodromy relation.
oh, the BCJ. Yes, the BCJs, the BCJ relations were proposed or conjectured by Brent Carrasco and Johansson in 2008, and then in 2009, Pierre van Hoof and some collaborators from Copenhagen, and also Stefan Stieberger wrote papers showing that you can derive the BCJ relations from string theory. And yeah, so string theory really knows a lot about field theory and
So they showed it only in the alpha prime going to 0 limit.
yes.
And we are saying that this is now the full string answer.
Yeah, so this is the full thing. All the alpha primes are coming from here. So for example, there is no alpha prime here.
So these people use pure spinors or RNS?
They use a general arguments. Like they had things like, well, if you put the vertices here and then you integrate and do stuff like that, and then you get they had some arguments like just from general principles. And by the way, the n-3 factorial, why it's n-3 factorial? The 3 there really comes from the fact that you fix it 3 positions, and then the freedom to get different color ordering simply correspond to the different choices of how you put the variables that you are integrating between these 3 points.
These 3 points fixed by eccentricity transform. These 3 points that are fixed.
Yeah.
They are fixed by the eccentricity.
Yeah, that's the main.
So you want to continue after?
Yeah, well, that's a good question.
Yeah, there is something you can do tomorrow. Whatever you do.
Oh,
It's coming.
Okay, doesn't matter, you can continue. What happened?
He's bringing it, but it's just a little delayed, so maybe 5 minutes.
Oh. So he knows that it's there.
Saying okay. Suppose you do on copy out, and you put massive scattering, it's still true.
3 level it must be true, right? Because it's a restriction of the equal before.
Cosonic string is nothing like it, right? No, no, I'm just saying.
No, there is actually, there is a paper that from last week by Oliver Slaughter. And Yuting Huang, and Hong if the guy is watching this, I'm sorry, I forgot his name. But these people here, they did an analysis of the type of integrals that appear in the bosonic string theory, and they could rewrite the bosonic string as in the same basis of integrals that you let's call f, and then use amplitudes plus some other chunk here that contains alpha prime and all that, but that was just a letter, and I don't remember all the details, and they promised to explain more about longer
It
paper.
doesn't factor out, so Yang knows.
What do you mean, factorize?
Can you write it in the form of the Yang knows amplitude times something else?
No, because there is a correction. Say, for example, the 3-point amplitude already contains its Young mules, and then already some alpha prime stuff here.
If we do it in RNS and only use the NS sector vortex operators, can we do a similar analysis?
In theory you can, but not in practice.
Yeah, so what goes wrong? Because the NS sector vortex operators are presumably simple, right?
Yeah. So
And we try to repeat the same kind of arguments there.
right, but you see that there were some points where simplifications depended crucially on the cohomology structure of the pure spinor superspace, and those type of manipulations are simply not there in the RNS. At least, well, I don't know how to.
Right. So if you use a normal BRST charge, it's not enough.
But the thing is that, well, so what was nice about the BRST charge here was that the BRST charge is simple, right? And this covariant derivative here is the same covariant derivative of the equation of motion. So this fact allows manipulations like you rewrite some term as q of something else plus other stuff, and then you integrate the q by parts, and you get all these kind of simplifying steps in your calculation, and those build up. For example, this trading identity over there, it's something that it's quite amazing that it works, and the fact that it works is, well, it's related to the cohomology structure of pure spinor superspace, the lambda 3, theta 5, and all that. Of course, there must be a clever way to handle the computations in the RNS, but it's very hard, and one of the reasons is that the vertex operators in the RNS, they are expanding in terms of the polarizations, right? So you are dealing with polarizations all the time, and So you cannot get rid of the polarizations, and because they are there in the vertex operators, whereas in the pure spinor they are sitting inside the superfields, and then the superfields you generalize to multi-particle guys, and then you generalize to Barrett's eddy currents. I did say, but the ends there are called Barrett's eddy currents, and then if you trace back what is happening with the polarizations once you go down that way, it's quite an amazing.
So in NS sector, I presume the vortex of the polarizations you could replace by AM, right? I mean, it's the vector part of the bosonic part of the gauge field.
Yeah.
Right? But you are saying that subsequent manipulations will not be.
Yeah. So for example, the string answer is written in terms of Young-Mills amplitudes, and just as a data point, 4-point amplitudes super-Young-Mills contains around 15 terms. So that's okay. People have computed using the RNS. 5 points, around 300 terms.
Counting.
Starting to get out of control, and in fact, the first computation was done in 2002. For 5 points, 5 tunes.
These 300 terms are coming from where? Different cyclic parameters?
No, just the one Young-Mills amplitude in the canonical ordering, like this one contains around 300 terms. Just the Young-Mills 5-point super-Young-Mills.
Yeah, but in string theory, of course, you will not have Feynman diagrams, right? You have.
No, not Feynman diagrams. The terms in terms of polarizations, stuff like this.
Oh, in that, yeah.
E4 and then E3, K2, stuff like that. So 300 of these guys that you need to carry around in every single step of your calculation. And there are 2 amplitudes in the final answer. And 6 points already gives you 6,000 terms, more or less. You see, it's more or less a factor of 20 each time you increase. So by the time you reach 8 points, you will be doing calculations with millions of terms, so around 2 million terms. And that's not the way to go, because the vertices themselves, they do not have this multi-particle structure, at least not in a way that people could understand right now. Perhaps there is. I'm quite sure there is, but it's hard to find. So So and by the way, you think, okay, I computed the guys computed the 5-point amplitude in the RNS. There was the computation of the 6-point amplitude, but the thing is that when you do this computation in the RNS and write the results as they wrote, you simply don't see anything there. It's just a mass of terms, and what's the structure? It's something that it's hard to analyze. So that's why it's very important to, at every single step, you need to have things that you can handle very simply, like this guy here, this numerator for a 4-point amplitude. If you write down in components, well, that's around, well, I don't know, 10 or 20 terms. And when you do this, that's something that you can analyze. You can even think that, well, that's a beautiful expression, It's only one term. It's you cannot analyze the BST variation and all that, but this guy contains information about hundreds of terms already. And these guys are simply there to help you in this language. So that is why I think it's very important to have the attitude that you consider these type of expressions as your final results for the amplitude. Say, for example, people write, well, the MHV amplitude is something like this, and then all the way down to, and they are happy because, well, it's compact and all that, right? And I think you could have the same approach here. You write, okay, the 5-point amplitude is this, and you stop there. It's you can as here you can translate back to polarization and momentum and those twistors and all that, but it's just a different language to talk about amplitudes. And I think that this language is very compact and it's in 10 dimensions, and in principle there must be a nice way to go to n equals 4 from that starting point. So it's yeah. So that's what actually I really would like to transmit this notion that amplitudes in the pure spinor formalism are these guys, those objects, and you should not try to analyze the component expansions. You can do, but it's not the way to go.
I think you use maximal supersymmetry. So
Yes. So the thing is that 10-dimensional superimposibility is quite unique in the sense that whenever you write something that is BRST closed in the cohomology and has the correct closed structure, you get the right answer. And that's how it worked at 3 level, and 2 years ago we also had the same approach for one loop amplitudes, integrands actually, in 10-dimensional superimposable theory. So for example, using this multi-particle superfields, we can say in a BCJ approach where you talk about cubic graph expansions, you can we have proposals that say that this is equal to V12 and then some object 3, 4, 5 over S12, and then the propagators L minus K12 square, L minus K123 square, and so forth. And then the idea is that for the five graphs of this type, and then plus the pentagon, if you get everything to be BRST closed, then you arrive at the correct answer. And we check that for the integrand at 5 points, and that was one of the things that I would discuss, how to what's the idea behind this proposal. And but one of the things here, for example, that well, I didn't explain what's that, but it's and the idea here is that in doing this calculation in this way, the BCJ relations come for free, in the sense that if you anti-symmetrize these two legs, say that the pentagon with two legs symmetrized, 1 and 2, and then minus 1 and 2 gives you the box, this expression here, and we have a superspace proposition for this pentagon. So in some sense, the theory in 10 dimensions is very beautiful. You can say, well, the 5.1 loop integrand could be a mess if you write down the polarization and all that, but in fact there are these 6 terms, and they all have this manifest property that you have the correct kinematic poles, and it's just beautiful. And also the 5-point amplitude 2 loops is being proposed in this way, and it also satisfies the BCJ relations. And we do that by simply looking at the string amplitude and getting inspiration from what's there. So for example, this T345 is related to the object that you obtained for the first time. It's that combination that appears in the 4-point amplitude and n, but now n plus cyclic. So this guy here is really coming from the OPE, where you get this OPE, you use multiparticle vertices, is V12, and then you pick D, D, N from the rest to give you that guy. And then that's associated to this propagator. And then that propagator in the field theory limit, you leave something like that. And then for the true loop amplitude, we have done the same thing. And now, for example, this guy here will be something like T123 bar 45, where these 4 slots are the same 4 slots that you got in the 4-point amplitude, something like A and then F, B, F, C, F, D, some permutations, and contracting all the indices here. That's the definition of that guy. So the multiparticle vertex there simply signals the fact that you got an OPE in the vertex, and then that's how things are progressing. And so yeah, all these things is to motivate studying D equals 10 as a simple example of a supreme theory. And we all know that in the end you can obtain n equals 4 from it, so perhaps it makes sense to study what's going on here. And then reduce to n equals 4, but reduce from simple expressions. Perhaps it makes sense to have this line of research, and so far it's kind of working, at least in 10 dimensions. Okay, yeah, so I guess I used my my extra time already.
No, no, so if you want to continue, yeah.
Oh, okay. Well, I can't continue because I think that the structure.
Okay, so you will come back in 15 minutes.
Okay, yeah. So if you have the energy. Okay. So this last part should hopefully be quick, but it's just that I would like to mention some nice structure that happens once you start to sum over all amplitudes in a sense that I'm going to explain now. So in the three-level computations from before, we had this object that I called MP, and which was defined by some V over S in some combination, right? So and this guy is associated to the multiparticle superfield A alpha, and what I'm going to show now is that there is a similar, well, exactly, it's an identical structure for all the other superfields, and these guys now in a calligraphic letter for all the superfields there. So it's a bit hard to write down calligraphic letters at the blackboard, but these are calligraphic versions of the superfields. And they are called Barnes-Gilly. Barnes-Gilly. I've been told that it's the proper.
Sorry, I'm not understanding. So in the first line, that MP has that kind of a structure, V by S.
Yes.
And then what did you put? Schematic.
Yeah. So for example, M312.
Yeah. Then what did you write? What did you mention
Yeah.
So
The structure, this structure here is actually associated to that guy, in the sense that this M12 is actually this guy here multiplied by lambda alpha. So that's the definition of M12. So
right.
the structure that I'm talking about is really about the A alpha.
Okay.
So it's A alpha that is being divided by the numbers. And in this
Cal K, what are you defining?
so it's a calligraphic K with a multiparticle label P that means the whole set of superfields. It's just a convenient way to talk about the whole superfields without specifying, okay, I'm talking about this guy or I'm talking about that one. I say now just KP to refer to the whole set.
Yeah, I mean you start the lecture today, you use this equation without calligraphy.
Yes.
What is the difference now? I don't
Okay, so the difference is that the calligraphic letters are the Barnes-Gilly currents, where you take the non-calligraphic guys. So in some sense it's like this. It's a calligraphic KP is equal to the standard KP with non-calligraphic over some poles. Sij, like that. Where KP without calligraphic is the same set, but without doing this. So for example, KP with straight typeface. It's straight A, and for example 1, 2 here, 1, 2 there. And then the calligraphic K, 1, 2 is the set where I take that guy here and divide by x12 and do the same with the others. So it's two definitions. One where it's the superfield, so these guys are the local superfields, local, and these are the currents. And to make things worse or better, depending on your point of view, I'm going to define yet another K, which is that one.
Just for for P more complicated, you will have several S factors.
Yes. In fact,
But it's this same common S factor that divides all the superfields?
yes. So in some sense, the K is meant to take out the identity of the superfields that we're talking about. When I talk about the Bernoulli current K12, I can be talking about any of the superfields there. It's just a it's just a definition to
Right. But for say M1, 2, 3, you had two terms with two different
yes.
set of S's.
Yes, so for example, K calligraphic K1, 2, 3 will contain something like actually it's A alpha now. 1, 2, 3 plus the other term. And then you do the same for the other ones. So for example, the next one is AM, and I do the same. This is really nothing, there's nothing not trivial here, it's just a definition of a name that you can refer to the collection of the superfields. Because I'm not sure if I'm going to be able to mention this, but by now there is an infinite set of superfields. We generalized the standard 4 to a whole infinite set, and then when talking about an infinite set, by referring to all the elements, you get into trouble because there are page limits for papers and all that.
Why is it the other ones are massive?
So the other ones are higher mass dimensions. So I can mention one of them because it's going to be related to the 3-loop amplitude. So the idea was to define something like that as a new guy.
So higher massive ones appear only for multi-particle levels or single particle level?
Not really.
Okay.
But the real power of the higher mass dimension guys are you can see it at the multi-particle level. Simply because at the single particle level, what this means is that this guy here, say for example, for 1, 2, it would simply mean, okay, I multiply what I get, the standard one by K12. So it's not that interesting, but I'm sorry. At the single particle level, you simply multiply by the momentum, and there's nothing else that you can do. But for example, for the multi-particle case, then you start to see some structure. extra structure. It will be some plus or minus A1 N W2 alpha and then minus 1 or 2. So you start to get some pollution coming from the nonlinearity here. And I'm going to, well, I wrote this example here. I'm jumping ahead a lot by mentioning this here, but I'm mentioning this particular example because it will be related to the tree loop amplitude in a non-trivial way. And in fact, that's one of the reasons why.
No, okay, so when you define the other set without calligraphy,
Okay.
there you have, you did not have massive states, fields. You had only these many, right? A alpha, A, N, W, P, and.
Yeah, they are the super mules
Yeah.
fields.
So why?
Mass.
Sorry, I'm missing something very simple, I think. So in this, but with calligraphy, why do you have massive fields appearing there? I don't understand.
It's not massive.
So without calligraphic also you could define these, right?
Yeah, so that's what I'm asking. But he didn't mention that.
So there is a higher mass dimension.
Yeah, it's
There is higher mass dimension with respect to the original theory.
Yeah.
Is that they are also in the
yeah.
original,
Yeah.
without calligraphy.
Yeah. Yeah.
They were there without, that also had infinite number of fields?
I can do that
You
for this guy here.
Yeah.
And I can do that for that guy, and I can also do that. And okay, you left, but it's a lot of nice structure, this guy here, and I'm going to talk about it now. Okay, so the definition of this calligraphic Bering-Schiele currents is this one. So it's a calligraphic version of the superfields, and they are defined by this equation here, where I divide, well, it's the standard, it's the Mandelstam invariant here, SP, and then I deconcatenate P into X and Y and sum over this bracket here, where the bracket means these guys for each type of superfield that you are looking at. So these expansions here are exactly the ones that were here yesterday, except that now everything is calligraphic. And there was going to be a difference in the W superfield, but so that's why I didn't write it. But you can look at the 1510 some numbers paper. And in particular, notice how the field strength is defined. The correction here is just a deconcatenation of A, X, and AY, and then there is no Mandelstam here, like there were yesterday, like there was yesterday. Okay, so this is a definition, and you can show that this structure here, where you divide by Mandelstam invariants, reproduce the same expansion of the binary tree that I wrote before. So, for example, from that recursion over there, you will get that K12 is S12 over K12 for K anything, any of the superfields, and then K123 would be S123, and now deconcatenation of the guys. So it's K 1, 2, 3 plus k 1, 2, 3. And now you plug this guy here, and then you see that you get the two terms that I wrote before from the binary tree. So the definition is actually the same as the binary tree, but yeah. So what's good about this Berens-Gilly current? Their equations of motion are more interesting. In this, they are easier in the sense that, for example, calligraphic guy is plus so the complicated mass with the power set from yesterday with the different momenta, the contact terms there, simply becomes a deconcatenation. So it's much simpler, and it's quite amazing because the equation of motion for the standard for the straight for the local superfields contain things like K1, 2, K3, K1, K2, and stuff like that, and they all cancel once you divide by the Mandelstam in the definition. So that's one equation. So you see it's exactly the same structure as the standard single particle case, but now with an additional deconcatenation term. And you can show the case you can write down the equation of motion for the other ones as well, but I'm not going to write everything, but there is also a deconcatenation there. And at this point you can actually do a mathematical proof of the equation of motion using this recursion, because you use a proof by induction. You start with the single particle case, and then it's possible to show that this is really satisfied in a rigorous manner.
So what is the reference for all this?
So the reference for this guy, well, it's safe to look at is 1510. I forgot the number, but it should be. It's okay. So there are now 5. So it's from October last year. There are 2 papers from October, but it should be okay, I don't have the preprint number. So, but it's called nonlinear gate transformations in the equal-stand super and mu theory in the BCJ duality. Okay, so that's these are the Berens-Gilly currents, and as perhaps a general remark, these guys are called Berens-Gilly currents, and you can show that. Well, people here know about the Berens-Gilly method from to compute amplitudes from 88. No. Okay. I'm just going to write down the formula that they had. They said that you can compute the Young-Mills amplitude by this formula here for gluon amplitudes. 1, 2 to n minus 1, and then you contract with the current with a single particle label, where these J's here are called the Berens-Gilly current, because it was in the paper by Berens and Gilly. And you can show that the Super-Mills superfield P evaluated on theta equals 0 and killing the fermions, setting the fermions to 0, is equal to the current that they had. But they had only this current here, and it was constructed recursively, but they also had instead of just cubic vertices like that, they also had a quark vertex.
Okay, so what is that first line? A1 to n? What is
Yeah,
that?
so this is the Young-Mills amplitude. Oh, the Young-Mills, not super. With this color ordering, it's given by a Mandelstam event with n minus 1, multiplied by the Berens-Gilly current with a vector index m contracted with here, mm, and then the labels 1, 2 to n minus 1 and a label n. That is a way to compute Young-Mills amplitudes, and it's as good as the BCFW or any other method to compute, and it's
There is a sum over m. M is the vector index.
yeah, m is a vector index, it's contracted, and n here is the label n November.
And doesn't this vanish as S? It's K1 plus K2 up to Kn minus 1.
Yes, but there is also the same guy here, the denominator here, the definition
I see.
there. So it's called the off-shell leg. So that's why they call the Berens-Gilly method the off-shell method, because in this current here, the guy associated to this the polarization associated to this M contains this propagator here, but it's divided here, so that's why we need to cancel.
But there we have a sum over x, y, which make p.
Yes.
Here it seems only one term.
Yeah. So but so how do you? Okay. And I forgot to say that you start with J M with a single particle label being the standard polarization. That's the starting point of this recursion. And the recursion is really like that. So for example, the current with J12 M is S12, and then, well, in their language, okay, it's something, it's like that. and then you need to use something.
Okay, in second equation a p n theta equal to 0, that what is that a p n? Which is equal to the current. That p is the multiparticle level.
Yeah, that's P. So
Yeah, what is a?
what is A? This A here? That's the superfield.
That's the superfield.
That's the superfield that.
According to your definition.
Yeah.
They were considering only young males, not super young.
Yes. So what I'm saying is that if you take our superfields, compute the do the recursion and evaluate the result at t equals 0 and set the fermions to 0. Then you recover the current.
So this is Carly, right?
Yes. It's a Carly. So that's why these guys are called Berensky currents. And an interesting thing that happens with these currents are the symmetries that they satisfy. So the curly K, you do A shuffle B, that's 0. For any, the shuffle product is familiar to, well, so for example, this symmetry here, well, it's called the Berensky symmetry. Well, it was, yeah. So, for example, K1 shuffle 2, that's equal to K1, 2, calligraphic K, right? Curly K, plus K2, 1. That's 0. And for example,
so shuffle keeps the ordering in 1 and 2 cells.
yes. So 1 shuffle 2 3 it's well, okay, so the shuffle 1 2 3 is 1 2 3 plus 2 1 3 plus 2 3 1, and then K at 0. And I have here, I guess, a general definition for the shuffle product, but intuitively it means that you simply shuffle all, you take all permutations where you intertwine the labels from the first set into the second set, in such a way that you preserve the order. So for example, 1, 2, shuffle 3, 4, you contain some 1, 2, 3, 4, you say 3, 1, 2, 4, because the 3, 4 order is preserved and the 1, 2 order is preserved, but it will not contain, say, for example, 1, 4, 2, 3, because this is not in the same order. And there is a recursive definition for the shuffle product is A shuffle B. It's A1, A2, A shuffle B plus B1, B2 to B shuffle A. It's recursive, so you need to specify the first one. It's with the empty set shuffle A, that's A. And the convention here should be clear that I'm writing the multiparticle A is these symmetries, and there is a proof for this symmetry, a combinatoric proof in the appendix of this October paper. And I could talk more about this and how it's related to the classical relation, but then I won't keep it.
Is that 5 steps?
What?
5?
Non-set.
No,
Yeah, no. Okay, so what are these Bernoulli currents good for? Okay, I'm running out of space. I'm not going to derive, but the nonlinear super-Mu's equations of motion, they appear in a paper by Witten in '86, and it basically comes from defining covariant derivatives like that. And he explains how everything comes from this equation here, and he obtains the nonlinear equation of motion, which are the following. I'm just going to write down one to save time. It's AM, and then plus anti-commutator of A alpha AB. So you see that the linearized version of the equation of motion that we were using so far simply dropped that term. The non-linearities were dropped, and that defines the linearized equation of motion. But the full equation of motion from Yang series is non-linear and contains that term. And similarly, there are non-linearities for all the terms. But now you do something interesting. You define a generating series of Bernoulli currents, and
So, what are you actually? Where are we heading to?
that's the
You never wrote that KP there.
that's what I'm going to do exactly now. So what you do is you define the blackboard boldface KP as a sum over actually it's and there is no P there. It's a sum. I'm going to write it in some schematic way, and then I will explain. It's the curly K and then TA, where TA, well, and just it starts with K1 T1 plus K1 2 then T1 T2, and actually it should be a free free guy here. But I think it's more pedagogical just to write the one here and do something like that. So that's the expansion and these and there are more terms. And these T's are the generators of a Lie algebra. So TA generators of a Lie algebra. And the curly K's are the Bransky current for any type of superfield. So in particular, just to make emphasize the point, we have this guy, we now have this guy, and so forth. And in 58, a mathematician called Ree proved that this series, when K, he didn't call that, he didn't use this nomenclature, but when K is a Bransky current, then meaning that satisfies that symmetry, then this K is a Lie series. What does it mean? It means that the product of the generators can be written as commutators. And for example, okay, so now I should also write that there is this guy here with 2 and 1. So it's a Lie series, and for example, it can be written as 1 over P and then K. Okay, so this notation here is a bit too compact, but I'm just going to TP.
This can be written in terms of structure constants
Yes. So in the end, everything is just proportional to a constant, a structure constant. So that's why for mathematicians it's important, because this guy belongs to a Lie algebra, and for example, for the first term here, it's easy to see that the mathematician was right, because K2 is unsymmetric, so these two terms become the commutator. And then when you sum everything, you will get 1 over 2, and then, but I'm not doing that in the sense of that this one should really be ij summed over ij. But the mathematicians are always right. And now we have a Lie series of superfields. And they are obtained by summing over all Bransky currents for all multiparticle states. And what's interesting about these guys is that now you can show, I'm not going to show here, but these guys solve the nonlinear multiplication math, the nonlinear field equations. So, for example, you get d alpha a theta, and now that there is no multi-particle label here because the whole the definition contains everything, and then it's where you can more or less convince yourself that this is true because when you look at some particular product of generators, this term here becomes the deconcatenation there, the two terms over there. So it should be commutator.
Often M or often beta?
Alpha beta. Essential.
Oh, okay, yeah. So yeah, it's anti-commutator. Yes, thank you. Oh, okay. So I wrote one over here. So
This is something.
Correctly below.
Last one.
It was written correctly below in that box. That's correct.
yeah, that's correct. Okay, yes. But you see that the composing Baranskili currents, they all satisfy that one. And then when you plug here and then you look at some TP, structure constant, then these guys become the deconcatenation, and you can show very explicitly that the nonlinear equations of motion are satisfied. And so, which is interesting because you started with the linearized superfields, computed the amplitudes and obtained these Baranskili currents, and now you sum over everything and then you recover the linearized the nonlinear equations of motion. It's all expected, but it's
No, could you please recall the procedure again? I'm confused. What exactly did you do? You had a starting amplitude.
yeah.
You said whatever you just said. Could you please elaborate on that?
Okay.
You started with some linearized what?
Yeah. So let's recall what we did. In the very beginning, we had the linearized superfields, say with a single particle label I, and the whole set K I. And these Ki's, the superfields there, they satisfy the linearized equation of motion. So it's that equation. You simply drop the nonlinear term, and you use this all along, linearized equation of motion. So it's the linearized superfield. And these guys are in the vertex operators. You don't use the nonlinear superfields in the vertex to compute amplitude. You do the computation at the linearized level. And it's standard knowledge, I guess, that you can start to study the nonlinearities of the theory by computing amplitudes with higher and higher points. But each computation that you do everything at the linear level, and then you start to see the nonlinear terms. And then you at some point you start to define the Baranskili currents like this, where every guy here satisfies it's constructed out of linearized superfields, and in the end you sum over everything in the Lie series, So we all know that the gluon field is something like that, right? It's in the Lie algebra. But now we are doing more. We are adding all the nonlinear guys, but by the theorem, this is also in some notation here. This is also proportional to just this guy because it belongs to a Lie algebra. So we sum it over everything here. It's an infinite sum, and when you do that, the composing superfields here, they satisfy the nonlinear equation of motion. So it's something interesting that is happening, and there is something else that there are lots of things that I could say about
So
this.
if one tries to do similar thing in the full strength theory, do you expect to get the high derivative corrections to the effective action?
It's something that I'm still thinking, and because you can imagine talking about doing things like this, where now this guy is the full nonlinear superfield, and then, okay, so the equations of motion are the same, so everything will hold. Say, for example, for the nonlinear BRST charge, you will get something like that as well. And it seems like everything works. But now at the nonlinear level. And, but I still really don't know what I'm talking about here, so it's just some preliminary observations. But what you can already see happening is you can define a generating function of amplitudes. And using these...
Just one point I wanted to clarify regarding this question is that you took this Young-Mills amplitudes and wrote that in terms of BG currents, right?
Yeah.
Instead of that, if you had taken full string theory amplitude, could you do a parallel?
Well, you see the Berens-Gilly currents are kind of independent from the notion of amplitudes. It's, for example, you could simply write down these out of nowhere, and then you can prove that these equations, these definitions.
But finally, the full nonlinear equation that you are getting,
yeah,
it has the information about the scattering amplitude.
In some
That's what you are getting now.
okay, no, I would say differently. That the scattering equation, the scattering amplitudes contain information about the Berens-Gilly currents. But the Berens-Gilly currents are objects that you use to construct the amplitudes, and not the other way around.
Okay, so I see. Okay.
So at this point here, it's you can view everything here as just purely mathematics. You want to solve the nonlinear equation of motion, and you write down these, and define the Lie series, and you get the solution for the nonlinear equation of motion. We all know that we arrive at these structures by considering scattering amplitudes, but in principle it's an independent thing. You just want to solve the...
And this thing is done where you said Witten's paper? 86?
Oh, yeah, the definition of these equations is in the paper. That's the same paper that Nathan mentioned yesterday. It's Twister or something, but I don't remember. Yeah, Twister transform in 10 dimensions.
But it's just covariant derivative. I mean, this is not, the paper is not about this. This is just.
Yeah, it's
just creating mills.
section of the paper.
Yeah, but not this argument.
No, which argument?
This argument, constructing that K and then Lie series and
Oh,
then
that's
summing all of them and then getting
okay.
the nonlinear equation.
Okay, that's this paper by Oliver Schroeder and myself. Okay, it's 01. It's from January this year.
Last year, January.
Oh yeah, last year, yes. But you should really look at the 1510 paper because we understood more about what we were doing. And as a final remark here, and I'm just going to say that you can show that, for example, Q on this V is equal to VV, and then that raises the question about, well, string field theory or something.
This is still at the particle level, right? This is super particle. These equations you are writing?
This is for the whole Lie series that is constructed out of BG currents.
For particle. I mean, as opposed to not string.
For yes.
Okay.
Yes. So for the multi-particle states of super-units.
Super-units. Okay, fine.
And this equation here you can see from here. You just contract lambda alpha, lambda beta, and then this term is cancelled by the pure spinor constraint. So that there is this thing here that you can see very roughly as coming from something like that. But what's the definition of that is remains to. There are subtleties that about it, but if you think about, let's think about this series for a moment, you realize that let's just compute this.
How is Q defined there?
Q is okay. So this Q can be. It's the linear. It's still the linearized Q, but what this equation means is that if you define a nonlinear Q as Q plus or minus V, so you simply, instead of using del d alpha, you use the covariant derivative, then you see that the vertex is closed. So the whole set of things is closed. So that's why everything that you know about the linearized superfields kind of translate to non-linear level. But just out of curiosity, let's see what this gives you. Well, I'm not going to do the computation now, but just compute the correlation function of three Lie series objects of V's. And then you see that this is a sum with, there is a coefficient here, but you basically get the sum over all super-induced amplitudes, where P is it's 1, 2, 3, it's a multi-particle label, and then trace TP. So you get the whole generating series of Yang-Mills amplitudes, and I didn't have time to do this, but in this 1510 paper we studied the theta expansion of this guy, and it's basically doing this, you basically get at the component level, you will get something like trace of AM, F, Mn, where all these guys are the Lie series, and plus the fermions, gamma D, and you can rewrite these as trace F squared plus W gamma plus W covariant derivative gamma M W, which is precisely the evaluated theta equals 0, because we are computing the component expansion. And this is, you get the 1/4 there, but this is the superimposed action. So it's also a consistency check that you are summing over all amplitudes and you are recovering the action in this way. It's very interesting.
And you just get the original action, or you get, oh, F is the capital.
Yeah, F is the Lie series of F's constructed from. Well, actually the first term is quadratic in the field, so it's the action plus things like that. So everything is non-linear and you are
What
recovering.
is written in front? Last equation? Before trace? What is that?
Yeah, it's the 1/4. The coefficients are correct in the paper, but not here, I guess.
This whole procedure has a generalization to supergravity?
That's a good question. Probably there is, and it's something that it's open.
Yeah.
There must be.
But it has to have infinite number of terms when you go to the non-linear level.
Yeah.
And this, it must be saying something about this Lie algebra also. It's a algebra of the Young's, right?
Yeah. Oh, okay.
That generator is?
What?
The generator T.
Yeah, it's.
The Young's generator. Right?
Yes. It's the same. It's the same guy that you use to expand the gluon field. But now you are generalizing to the whole Berensky series. And just as a final, so I promise this is the final comment. We see that the Lie series has this structure where this guy satisfies Berensky symmetries, and this by very definition is satisfies Jacobi identity symmetry. So it's satisfies Lie symmetries. We call that Lie for historical reason, but it should be Jacobi symmetries. But that's the general structure of a Lie series. And just look at what we have here. That's why I didn't erase that blackboard. We have the structure of a VA contracted with these functions there, which I'm going to call ZA. And this, as we were discussing yesterday, satisfies all the Lie symmetries. And this, lo and behold, satisfies Berensky symmetries by partial fractions. So the string correlator is also telling you that the Lie series structure is there somehow. So you can rewrite that as in a more abstract way as this, and then B transpose, Z B transpose, and then Vn. you instead of these worldsheet functions, you have the derivative of the log of the prime form, like Narayan was telling us. And this is a replacement of the Zij functions, right? But these, so, and the OPEs that you're going to compute at one loop level, they work the same as at 3 level. So you will get some structure like this. But the functions here will be constructed out of these guys. And these guys do not satisfy the Bernoulli symmetries as these guys satisfy. So what's going on? It would be nicer if the functions here were something that would satisfy the Bernoulli symmetries. And by computing the 6-point function, we actually observe that say I'm going to call this Gij1. We observe that these guys here, for example, at the 6-point order, are corrected by a function which is non-singular in the surface, and it comes from expanding the Einstein-Kronecker series, the holomorphic one. We did that in December last 1412 something. We analyzed the kind of functions that you get at genus1, and we found this function here. It's basically a difference between del 2g minus the Weierstrass function, in such a way that the coefficients here means that when the vertices collide, you don't get any singularities, so it's regular. But this combination here satisfies the Bernoulli symmetries, and then the one loop amplitude is also being written as something like now this function z1 to 3 at one loop, and you get the same structure at 3 level. So you're already getting information about these non-singular functions. So okay, there's a lot of stuff, but let me stop here.
We explicitly construct this G2.
Yes. Yeah, G2 is basically this. It's where this is the Green's function, and this is the Weierstrass function. So the Weierstrass function is something that has a double pole. This one also has a double pole, and they happen to cancel the limit. So and these guys, there is an infinite set of these functions that come from expanding the Einstein-Kronecker series. So there is something going on. That's the one loop amplitudes will probably mimic the structure of the 3-level amplitude, and it's interesting. And we are just seeing this kind of structure because we are going to the multiparticle level. It's something that you cannot simply see by being content with the 4-point amplitude. It's yeah.
This is one loop on annulus?
Yeah.
One loop.
No, it's the actually, well, it's the annulus and the Möbius strip and the non-planar, the cylinder, the non-planar cylinder. Yeah, that you can define them, and yeah, this is actually related to the anomaly cancellation. But this is still work in progress. But it's nice because the mathematics is repeating itself.
The prime form will look different than what Narayan wrote, right? He was writing something else.
Well, no, yeah, but that, no, it's basically theta over theta dot, something like that. There are a lot of things to do.